This is still when the second example. Now at this point we have found the family of solutions u sub n of x comma t equals to d sub n times sine of n pi x over 10 times e to the negative 3 times n squared pi squared over 10 squared times t. And of course, so these are the family of solutions, and that is why I wrote subscript n here. Basically this constant depends on your n value. Now since I have a family of solution and our original PD is a linear one, from the superposition principle we can construct another solution by adding all those solutions in our family. So to denote that, you have a summation that goes from 1 to infinity of d sub n times sine of n pi x over 10 times e to the this term. Okay, great. So our final step is to figure out a value for dn. So at the moment we have used both boundary conditions, but we did not use the initial condition, and the initial condition says u of x comma 0 equals to, it's a piecewise defined function from 0 to 5 your initial temperature value equals to 3, and from 5 to 10 it equals to 0. Okay. So if I evaluate this solution at t equals 0, you will get we have dn times sine of n pi x over 10 times e to the, now if t equals to 0, then you have e to the 0 which is 1, great, but this equals to the piecewise defined function at time t equals 0. Okay, great. So now again we are going to use the same argument. This left hand side is a Fourier sine series, and these d sub n are the Fourier coefficients, and the function that generates this Fourier sine series should be this function. And there is another important point, that is we get a Fourier sine series for odd functions. Okay, so right now we have an interval that goes from 0 to 10. Now let us construct the odd function that generates this Fourier sine series. Okay. So first we are going to focus on the positive x values. Let us say x goes from 0 to 10. So here 5, here it is 10. Okay. So somewhere here we have 3, and after that it becomes 0. Now we need to construct the odd function. So remember, if you have an odd function, then f of negative x equals to minus f of x. So in other words, we have to multiply each of these values by negative, each of these y values by negative 1. If we do that, you will get negative 3 here and then 0 here. Okay. So now my interval goes from negative 10 to 10. Therefore, your p value equals to 10. Okay. Now the formula for these Fourier coefficients is d sub n equals to 2 over p, which is 10, times the integral that goes from 0 to 10 of, let us say, this function u of x comma 0 times sine of n pi x over p dx. But u of x comma 0 is a piecewise continuous function. Therefore, we have to split this interval into two parts. So, we have 1/5, 2 over 10 is 1/5 times the first integral goes from 0 to 5. From 0 to 5, your function u of x comma 0 equals to 3. So, yes, 3 sine of n pi x over 10 dx plus from 5 to 10 my function equals to 0. Therefore, this entire integrand becomes 0. If you integrate 0, you should get 0. Okay. Now, let us simplify this integral. So, if you do that, you should get, so we can pull out this 3 from the integral sign. So, we have 3 over 5. Integral of sine is minus cosine the angle n pi x over 10 over this constant term which is n pi over 10. Lower limit is 0, upper limit is 5, and if you apply this limit, you should get dn equals to minus 6 over n pi times cosine of n pi over 2 minus 1. Okay. Now, let us see. So, if you apply the upper limit, you will get n times pi times 5 over 10, which is n pi over 2, minus if x equals 0, you have cosine of 0, which is 1, but please note that we have factored out this negative 1, that is why I have negative 6. Okay. Great. So, if you simplify this, you should get this expression for dn. So, this is your dn. Now, finally, we can update our solution. U of x comma t equals to summation n goes from 1 to infinity, dn equals to this negative 6 over n pi times cosine n pi over 2 minus 1 times sine of n pi x over 10, okay, and times this exponential term e to the minus 3 times n squared pi squared over 10 squared t. Okay. Okay. With this, we finish the second example. Okay, so this is the final solution of the one-dimensional heat transfer problem. Okay, thank you.